There we go. I think I got everything set up. Hi, everybody. Welcome back to Chem 161. Let me turn down this music here. Hope everybody had a good weekend. Welcome to week 10. This is the last week of the class. I mean, not counting finals week. This is the last class week that we will have lecture. We still have stuff to do next week. Well, I mean, you do. I don't. Other than grade everything, which definitely counts as stuff. Let's see. Our agenda is kind of light this week, thankfully, except for one very important thing at the end of the week. So, on the Canvas website, I have sent out an announcement that talks about course evaluations. So make sure that you have seen that announcement. If you haven't, you can check your email for that, but you know what I can do? I could just get it on the screen real quick here. This will work. Announcements. So yeah, if I go here real quick, you'll notice that this announcement right here is available. I don't know if it completely fits on the screen, but we can make that fit on the screen. So there's a link that you're going to need to follow anyway, so whatever. When you click on this link, it will take you to this website, and it will give you a bunch of just stuff that I want you to follow the directions for. So, for example, click down here where it says Campus Lab Student Login. And then you'll log in. You use the same login information as Canvas. For some reason, unbeknownst to me, this process doesn't work for a lot of students. And like they tell you about like, oh, if you haven't done anything or it doesn't work or something like that, use this link down here to reset your password. Your My ABCC page also has it, and it's in this list down here. And then they tell you about what the idea form is. You don't need to look at any of this stuff. You're just going to answer the questions. Is your password being outdated? So I've had people tell me that they were able to log into everything but Campus Labs specifically. So that's definitely a possibility. But my understanding is that Campus Labs is just bad. Because every quarter I have trouble with this. And the reason that I'm showing you all of this live on the video is because I cannot resolve any password issues that you have. I don't have access to your password. I don't have access to your login information. I don't have access to much of anything from your end. So if you run into password issues because you're doing this on Friday night before it's due, you're not going to be able to access it. So make sure that you try and do this early in the week. It closes Friday. I don't know if that means Friday at 11:59 p.m. or if that means Friday at noon. They don't tell me this stuff. Oh, it says right here. It literally says right here in front of me. Evaluations close Friday, June 11th at 11:59. You might be asking yourself, well, wait a second. Right there it says they open on May 17th. Yeah, we don't want to talk about that. The reason that I put the evaluations at the end is because if everybody scrambles to do them, I actually get evaluations. Whereas if I've done this before, I open it on May 17th, everyone's like, oh, I have all quarter to do it, and then nobody fucking does. So I think 2 quarters ago when I had evaluations done, I went and looked at the numbers, and in one section I had 24% of students do it because I gave you a month. So now I give you 3 days. We're going to try the other end. And I know that I already saw in a few of my Discord channels, students were saying, like, oh my god, evaluations, let's do the evaluations. Please, no witch hunts. Do not pressure people into doing evaluations. There may or may not be reasons that students, however valid or invalid they may think that those reasons are, that they would not want to give a course evaluation. I do want to assure you that I don't read the results of your evaluations until after grades have been posted for the quarter. And in fact, in some cases, I don't even read the evaluation comments at all until, like, I get to campus. So, like, I haven't seen the ones from last quarter because they used to give out physical copies. I can access it online now. I guess if I wanted to. I had to dig in to figure it out. Campus Labs is terrible for me too. Like, it's super frustrating. Why is this the thing that is giving us extra credit? Because if I don't give you extra credit for doing evaluations, you won't do it. Like, that is just evidence that I have, because if I don't bribe you to do course evaluations, and you should still do them honestly, if I don't bribe you, I won't get feedback. Are we going to review exam 1? Yeah, we're going to review that during finals week. I mean, the content, I am never going to unlock exam 1 for what it's worth. So yeah, that's a very pragmatic question to ask. Like, why is this the thing we get extra credit for? It's purely a bribe. Like, I will be transparent about that. Like, nobody will waste any time. Oh, that's 20 minutes. I could be spending that studying for quiz 4. Yeah, I totally get that. Like, that is very valid. But this is something that the college makes me do. Personally, I think that the evaluation thing that we use is kind of a waste of time. Because it asks you a bunch of questions about things that aren't relevant to this class, and then I basically get evaluations that say the following: Wes was the best teacher I've ever had. He transformed my teaching or educational experience 3 out of 5. So this is your chance to treat me like an Amazon product, also, if you'd like that. What am I looking up now? Because somebody asked for something. When is the due date for the last lab? So that's on the syllabus. So make sure that you look at that. But I do also want to very briefly talk about the last lab. The last lab is, in some ways, it's the easiest lab because there's nothing new. And in some ways, it's the hardest lab because it's a review of all the labs that you've done, more or less. So we'll put that on the screen too. So lab number 5 is called the analysis of wine. What we would have been doing in the actual laboratory is that we would give you a sample of synthetic wine, although we could actually use real wine to do this, supposedly. It's just that real wine is expensive. We give you synthetic white wine, and then we ask you to tell us how much booze is in it, so how much ethanol, how much tartaric acid is in there, and how much sulfur dioxide. And the way that you're going to do this, you should immediately know what to do when I talk about these. So, to determine ethanol, we mix ethanol with a sample of ammonium cerium nitrate, and what ends up happening is you get this reddish-orange substance that can be detected using Beer's law. So I have run a standard set of solutions through a Beer's law absorbance spectra, and then we measured, doing the same process with Chardonnay and Riesling wine samples, what their absorbance was. So you should be able to tell me how much ethanol is in there. Very important that the unknown samples, so the Chardonnay and Riesling right here, these are diluted by a factor of 5, but only for part A, so that their percent ethanol is between 1 and 5 in the standard. So whatever Chardonnay and Riesling is, whatever ethanol you get it to be, times it by 5. Because there's no way that wine is like between 2 and 3% ethanol, right? We had to dilute it in order for it to fall within this range, so that it was within the range of Beer's law. So part A is do this analysis, do it using Beer's law, just like you did for lab number, I want to say 3. Okay, no problem. Part B is a titration, and you did a titration in lab 2. Here's the data. The only real trick to part B is that the units that we ask you to give us are a little bit strange. And so what I want you to do is I want you to measure your concentration in what's called mass volume percentage. That means figure out what the mass of tartaric acid is in this sample, then divide it by the number of milliliters there are. Now, as a hint, you should get an answer that is between 0% and 2% or so for mass percent. or mass volume percent. And then finally, the last part is SO2. This reaction looks way more complicated than it is. All you really need to know is that SO2 and I2 react 1 for 1, which means that the number of moles of SO2 in the solution is going to be equal to the number of moles of I2, and you're titrating using iodine. This just tells you what's happening. This is a very specific reaction that we do in the lab all the time. Iodine titrated with a starch indicator turns dark blue. Iodine also reacts with sulfite. So if I have this in my solution, which is used as a preservative in wine, and I add iodine to it, it will react and the I2 is gone. We actually don't give a shit about any of these components because we're not testing for them. What we're actually testing for is iodine. But iodine will react and disappear in the presence of SO2. When all of the SO2 has been reacted, any leftover I2 just hangs out and then reacts with our indicator to turn blue. So I have written down the volume of the iodine that is needed before it turned blue, which means that I needed the difference between these volumes worth of iodine. Here's its concentration. You can figure out how many moles that is, then you know how many moles of SO2 there are. The units that I want you to consider for this expression are for milligrams per liter. Here's the hint for your answer range. You should get something between 20 and 40 milligrams per liter. Oops, that's not on the screen. Now, there is a lot of work to do here in terms of like things you need to do calculations for. But there's nothing here that you have not done. So when you go to the lab page, where am I clicking? I'm clicking here. To go to the Google Sheet, you're going to see something that looks like this. And it's just blank. And this is it. So I'm going to ask you for 3 things on each page. Your answer for each of the wines. Tell me what you did in a few sentences. And then finally, in this big blank space at the bottom, do whatever the hell you want to answer the question. So if you have to do a Beer's law plot, make a graph. If you have to do a titration, put a bunch of tables with numbers in them. Be as clear and exact as you can be. So like indicate what everything is. If I look at your data chart down here and I'm like, I don't know what's going on, I won't give you any credit for it. Note that each page is worth 5 plus 2 plus 3 points, and they're all like that. So this lab's actually worth 30, but I'm only grading it out of 25. So if you get, it's like the exam. If you get more than 30 points, you get to keep the extras. So here's your actual extra credit. If you do this lab perfectly correct, I'll give you 5 points extra credit. If you don't do it perfectly correct, then you'll just get normal credit. So you can still get up to 25, of course. This lab is due on the date indicated on the syllabus, which I believe is the day after the final exam. So let me look at that real quick. It's due the day before the final exam. Okay, so this lab is due a week from tomorrow, which would be the 15th. So we'll just throw that up here. Oops, that's not the right thing. This one? Yeah. So lab worksheet number 5 due Tuesday 15. That does put last call on the day of the final exam. Don't put it off. Like, if you want to work on the lab after the final, sure, I'll give you that option. Excuse me. I do need the labs in at that point. Otherwise, I will never get them graded before grades are due. So that's the reason for the deadline. All right, let's get started on the rest of the lecture. So we have one more section to go in Chapter 4, and then there's this little blurb at Chapter 10 that we're going to talk about. So we're going to do geometry today. Geometry is sort of the whole point to Lewis structures, and I know a lot of people are asking questions about this in the Discord. Like, man, Lewis structures kind of suck. Like, why is it that, like, we get this method to do everything and then it sort of all falls apart? And the answer is that we're trying to model our structures so that they resemble what we see in 3 dimensions. Because we can do things like X-ray diffraction and other spectroscopic techniques. So, like, IR tells us stuff about bond orientation in space and types of bonds and stuff. NMR does that too. You're going to learn about all these spectroscopic techniques in 163 and then the 260 series. But the point is that molecules obviously exist in 3 dimensions like we do. And we can measure all of their properties, but drawing Lewis structures just sort of however we want to isn't going to be super helpful if the structures don't match what we see in reality. So, for example, we've been drawing things that have 4 bonds coming out of them in straight lines like this, and it turns out that this is totally a generalization. And we're going to have to change that a little bit today. So, there are 2 things that we care about in terms of measuring properties of molecules with regards to their structure, and the first one is their bond length, and the second one is their bond angle. Bond length is measured in angstroms or picometers. An angstrom is, I'm going to assume that it's a Swedish unit or a Dutch unit, due to the little circly-do over the A. Why is this a thing that is happening? Why are there so many cats yelling at me? It's week 10 and even my pets are upset. So the bond length is measured in angstroms or picometers. So if we measure it in angstroms, we get a number between like 1 and 4. So that's why angstroms are used specifically for bond length. Picometers, when you measure bond length, you're going to get a distance between like 100 or 500 or something like that. And then the bond angle is just the number of degrees between any 2 bonds coming out of a molecule. So you could see up here that for formaldehyde here, the bond angle is 118 degrees. Now, that's not a very regular number. In fact, if we had something with a triangle, what we would anticipate is that its bond angle should be something like 120, right? Because there are 360 degrees in an entire circle. So what we're going to do is we're going to try and figure out what these angles are, and then explain why the numbers deviate slightly. So we'll get to that later. Now, because all of our molecules have some sort of geometry to them, and because they consist of bonds constructed by electrons, we can predict the shape of those molecules. And so the way that we do that is to assume that if all of our bonds are made of electrons, they repel each other. Now, they don't push each other so hard that the molecule falls apart and all the bonds dissociate. What they instead end up doing is they just orient themselves as far apart as possible. So if I have 2 bonds around something, the bonds are going to push apart such that they don't end up like this. So my bonds would not do this. This would swing around, and my result would be something like this. And the bond angle I would then have should be 180 degrees. And then for a triangle, it should be 120 degrees, and then so on and so forth. So this is called Vesper, or valence shell electron pair repulsion theory. Now, that sounds like a mouthful, but you actually know what all those words mean. Valence shell means we're only using electrons in the valence shell, in other words, the bonding electrons. Electron pair, well, all of our electrons are paired together, either as non-bonding pairs or as bonded pairs. Repulsion, electrons repel each other. And then theory, because this is explaining why our molecules have shapes. So Vesper says that there will be a very regular selection of shapes that can happen. Now, first we need to consider what sorts of things will repel each other. And so I'm going to put these on the screen, and then we're going to go to this. We're going to go draw this. So on my canvas right here, if I were to draw a molecule, so I'm going to have, here's my central atom right here. And then coming out of that, I'm going to draw a bond to another atom, and a bond to another atom. And then I'm going to also put electron pairs on the central atom. So this is basically water, is what I'm drawing here. If I asked you, point at all of the electrons around the central atom, you would go, okay, well, there's some in this bond. There's some in this bond. So these are my bonding electrons. And then we have some electrons over here and over here. So these are my non-bonding electrons. So all of these electrons take up space. And what that means is that each of these pairs of electrons is going to repel the other. So I need to count the number of spaces that contain electrons. So in this instance, there would be 1, 2, 3, 4. So there would be 4 electron groups. So we're going to call these electron groups. An electron group is a space that contains electrons. Notice that I'm using the word space. Our angle is defined by a vector addition with forces being proportional to the effective. We're not going to be that complex. That's going to be polarity, though. We're going to do that later today. Don't worry about bond angles just yet, because it's a lot simpler than it seems. So we're gonna call any region of space that has electrons in it an electron group. So what are electron groups? They are, let me write it this way, bonds connecting two atoms together, or non-bonding pairs of electrons. So one of these two criteria must be met. Now, if I were to have a different molecule, like, say, formaldehyde, like we had above, here's my molecule, and I would ask for the central atom, where are the electrons around it? So I would go, okay, there's electrons in this bond here, electrons in this bond here, and then I have this double bond. Well, they're both connected to the same atom. You'll notice up here that I said bonds, plural. So if there are any number of bonds connecting two atoms together, we're going to count that as in the same place, and so I'm going to circle it as the same group of electrons. So there would be 3 electron groups around the central atom. And you're going to notice that we only care about the central atom here. So these electrons, so these are not the central atom, and so we ignore them. So don't count things on extraneous elements. We only care about the central atom because those are the things that are going to determine our bond angles, right? The other stuff is too far away. It would determine its own bond angles over there if other bonds existed. So again, to refresh, electron groups are either bonds, single, double, or triple, connecting two atoms together, or a non-bonding pair of electrons. And we will be considering these on the central atom for each of our molecules. So in the top example, I got 4 electron groups. In the bottom one, I got 3 electron groups. The number of electron groups that you determine is going to influence the shape that you get. And so that's going to look like this. So we're going to come back to these names in just a second, but what I need to do first is turn off my alarm because it thinks that I need to wake up for my afternoon class. So I need to click on that. There we go. I'm like trying to get the tool out of the PowerPoint thing. Here we go. So we'll turn this on. So this is called the Phaet Simulator. I don't know if everything is actually posted there. What I'm going to do, though, is I'm going to paste this link into the chat in case you want to play around with it. And so what this does is this, you click on the model here, and you can't see everything, so I do need to adjust this. What this is going to do is it's going to count the number of electron groups. That's the bottom of the screen. There we go, that's good. It counts the number of electron groups. I mean, you could visually do that. You can add as many groups as you want. There you go. And you can see that the shape of the molecule changes as we add things. Now, this does not care about the octet rule or any reasonable number of electrons. So you could put like 3 of these and then a double bond in, or maybe just fill it with triple bonds because this poor molecule, right? But you're going to notice that depending on the number of entities that are present, so I get a shape that is very regular. So whether this is a bond or a triple bond or an electron pair or whatever, the shape that I get looks like a line, right? And the angle, let me put the angle here, is always going to be 180 degrees, you'll see. Because there are 2 electron groups, one pointed in this direction and one pointed up here. Now, if I do this, there won't be a bond angle because there isn't a bond here. But these are still electron groups that are 180 degrees apart. So we're going to assign a name to any central atom that has 2 electron groups around it. We're going to call that linear. And the bond angle that a linear entity makes is 180 degrees. So we're going to write that on the sheet here, which you can't see just yet. I'm just writing down all the remaining bond angles here real quick. So what you're describing is not actually a circular arrangement. You actually get a hexagon, but we'll talk about that in at the very, very end of this lecture slide today. All right, so we've got our linear here. Let's go like this. Now, if I were to put a third entity in here, no matter what it is, so if I put this in or this in, you'll notice that the things that are left over form a triangle. And it doesn't matter how I do this. What are the angles in a triangle? 120. So we're going to call this based on the shape that we see. It looks like a triangle, and it occupies a flat plane, as you can see when I rotate it this way. So we're going to call this trigonal planar. Any entity with 3 electron groups around it will be trigonal planar. Now, for 4 groups, you might think, oh, I'll just make a cross or a plus or a whatever, right? But it turns out that this is where the 3 dimensions comes in. We don't end up making a plus because the angles for a plus sign are 90 degrees, right? "90 degrees is not the optimal electron arrangement. It turns out that the best, furthest possible arrangement of electrons apart from each other is if these 4 bonds are arranged in a tetrahedral pattern. And so what is a tetrahedron? Well, it looks like this. It's a little pyramid with a triangular base. If you've ever played Dungeons and Dragons, imagine a D4. That's the tetrahedron. Each of these hydrogens is at the corners of that, and then this carbon is trapped in the middle. And all of these angles are 109.5. And it does not matter if I remove one of the bonds and replace it with this, I still end up with 109.5 degree angles. Or if I make it a double bond or whatever. This actually doesn't simulate the effects of angles, other than just like calculating what the exact number is for a regular shape. So 4 electron groups around the central atom gives you a tetrahedron. Angles are 109.5. What about 5? 5 gives me a very weird shape. So you'll notice that there are 90 degree angles for everything top to bottom. But if I look at this from above, I have a trigonal plane in the center of a line type arrangement. So first of all, the shape that we're going to call this is called trigonal bipyramidal, because if you look at these 3 triangles in the plane, I could make a pyramid out of that on top. I could do the same thing on the bottom here, make a pyramid pointing down. So we call that trigonal bipyramidal. And the angles in this are all 90 with relation to the equatorial triangle part, which is this right here, and the top or the bottom. So all of these angles are from the equator either to the top or the bottom. They're all 90 degrees. But if I spin this around, that's not the direction I intended it to go, but that works. And look at this axis head on. All of the equatorial atoms or groups have 120 degree angles with themselves. So the 5 electron group one is the weird one. You have 90 and 120 are the bond angles. And you got to know where the 90s appear and where the 120s appear. I apparently distorted it, so now I'm trying to get them both on there at the same time. And then 6, everything is 90 degrees, very regular. In fact, this is your D8 if you've played Dungeons & Dragons. These are the points of the D8. Because there are 8 faces on it, it's a D8, there are 8 numbers. We call it octahedral. Hedra meaning a face of the solid that is made for this. So that link that I posted in the chat there, play with this, spin these around, so you can get a feel for the shapes, but these are the basic shapes. And so you can just add in groups and do whatever you want to. Now, you'll notice that I have not checked this box yet. There's a reason for that. We're going to get to that in just a second. So there's all my bond angles. We're going to call these shapes electron pair geometry. You may also hear these called Vesper. I always misspell Vesper for some reason. I spell it Vesper. Vesper Geometry. Though I try to call it electron pair geometry, just to be consistent with your textbook. And so what this is basically a template. This is just our way of predicting what family of shapes this molecule can belong to. So for instance, if we go over here, I want to get all of these on here real fast. If I had a molecule that looked like, say, oh, I can't actually use this real quick. Hold on. My Photoshop glitched out. If I had a molecule that looked like, say, this. So I drew this as my Lewis structure. The first thing I would do is I would say, okay, how many electron groups are there? Well, there's 1, 2, 3, 4 electron groups. Around the central atom. And so what that means is because there are 4 groups, the electron pair geometry is going to be tetrahedral. So the actual structure of the molecule would conform to a tetrahedron. So if I had a tetrahedron, where this is my central atom, and then these are the groups around it, I'm going to try to draw this as good as I can so that it looks like a tetrahedron. And then we'll put these just dotted lines here. So this is what a tetrahedron would look like. Now what I could do is I could say, well, nitrogen's the central atom. I've got a chlorine, a chlorine, a chlorine, and an electron pair. And that's what my molecule would look like. That's the shape it would take. So you can think of the Vesper geometry as just a template. If I had a molecule that had 5 electron groups, such as, let's see, I think this will work. You get something that looks like this. No, this actually won't work. That'd be 6 electron groups. Sorry, hold on. 35, 8, 16, 24, 32. Yeah, that won't work either. All I'm thinking of are square planar ones. I have to go look one up. We'll see one that has 5 electron groups later. But anyway, we're going to use these as templates, and then you just paste the atoms or the electron groups or whatever they end up being in the circles. So you're going to be asked to look at a molecule and give me its electron geometry. Now, something you'll notice is that if we go back to here, that if I start replacing things with electron pairs, we've sort of drawn these electron pairs to be really, really big, haven't we? So this is the molecule that I drew on this right here, right? But electrons are supposed to be these really, really teeny tiny things, especially relative to the entire atom. So if we go like this, boop, this is more akin to like what we would actually see, right? Because the electrons exhibit a force, but they're very, very small. And so when I look at my molecule like this, it doesn't really look like a tetrahedron anymore, does it? And that's because the influence of the electron pair is there, but it's tiny, so it's not easy to see it. So that's where this comes in. The molecular geometry, it says molecule geometry on here, that's why I misspoke, is the geometry that the shape takes based on the presence of electron pairs. And you'll notice that the name is different here. And so what we need to do is we need to actually build all of the possibilities and see what they look like. And so I'm going to use this to do that, but what I need to do is I need to resize it. So hold on just a second here. So I'm going to put this over here and give myself a little more space. And then what we're going to do is we're going to make a giant list of all the possibilities for... Why is this... Why did it group the layers? There, that's fine. Okay. What we're going to do is we're going to make a list here, so... Alright, so I actually need to change this just a little bit because I ran out of space. Because I do want to indicate what the Vesper geometry is. Alright, so I should be able to play around on this screen, and now everything will look the same to you. I need to actually move this over a little bit. Alright, now you'll notice that regardless of whether we have bonds in here, actually I can only have two, or an electron pair in there, we're always going to make a line, right? So whether I have a bond there or an electron pair, it still looks like a line, whether you can see the electron pairs or not. So anytime you have two electron groups, the Vesper geometry is going to be linear, and the molecular geometry is also going to be linear. And so this doesn't matter. We're going to skip it. All right, we'll separate that out. So the next one we're going to look at is 3. If I have 3 electron groups in here, they form a triangle, and we call the Vesper geometry trigonal planar, just like we said before. Now, if electron pairs are invisible, then adding one in here changes my shape, doesn't it? So if I have 3 electron groups, but one of them is an electron pair, my shape is now different. This is no longer a triangle. In fact, it's more like a line, but it's bent. We're going to just call it bent, right? So if I have an electron pair in here, the shape changes as opposed to if I didn't have an electron pair in here. Now, if all of your electron groups around the central atom are just bonds, the electron geometry and the molecular geometry are going to be exactly the same thing. And that seems like a sort of, well, okay, they look identical, so duh. Sorry, more cats need to get squirt bottled. But if I have one electron pair in there, the term that we're going to give for that, and we'll hide the electron pair, is it's a bent line. We're going to call it bent. So let's do that. So there's the 3 family. All right, so we'll put this back. Let's go to 4. So we just said that 4 is tetrahedral. And if everything is bonds, the molecular shape that we're going to give it is the same as the Vesper geometry. But what happens when I start replacing these with electron pairs? What shapes do I get? Well, let's try that. So I'm going to remove one of my bonded atoms, and we're going to replace it with a pair of electrons. And I'll just spin it around. It seems kind of weird to be pulling on these like that. Like, it seems violent, almost. We're going to get rid of the lone pair so that its influence is felt but not observed with our eyes. And you'll notice that the shape looks kind of like a tiny squash pyramid, right? We're going to call it that. Trigonal pyramidal. Okay, let's do that again, but with one more electron pair. So we'll get rid of another bond and put another electron pair in. And you'll notice that when I hide... So let me arrange them so it looks like a tetrahedron again. We've just got these electron pairs here. But when I hide the pairs, this looks like something we've seen before, doesn't it? This looks like bent. It just has a different angle. So we're going to call it that. Bent. My trigonal pyramidal kind of got scrolled off the screen there. Let me fix that. There we go. In fact, let me just do that so I can fit it all in there. All right, so that's 4. So for trigonal bipyramidal, let's put all of the... Oops. We do want that shown. Sorry. Let's put all of the bonds in. So there we go. So there's our trigonal bipyramidal. Now, if I start removing electrons, that shape's definitely going to change. But the first example is just what is it before I remove any electron pairs or any bonds and replace them with electron pairs. But now if I do that, you'll notice that the position that it tries to adopt is one of the ones on the triangle. And there's a reason for that. And we'll talk about that in a little bit. Electrons repel just as much as bonds do, despite their tiny, tiny size. Because they're more localized, they repel extremely effectively. And so they want to go in the spot where they can avoid... I keep tugging on the wrong thing, and it's changing the shape. They want to go in the spot where they are the furthest away from everything else. And so that's on the triangle, because 120-degree angles are present. So by going onto one of the triangle spots, on the equator here, this electron pair can be farthest away from everything else. Now, the shape that we get when we do this, I'm trying to spin it around so it looks like a seesaw. There we go. So now it looks like a seesaw. Can you see the seesaw? It's really hard to do this, especially when the fulcrum keeps moving. But yeah, chemists are not very good at names, it turns out. So we called this one seesaw. Are we only going up to 6 because of the limit of 6 bonds? There actually isn't a limit on the number of bonds. You can go past 6 bonds. However, past 6 it becomes rare because you run out of space. You just can't fit that many things around an atom effectively. All right, if I have 2 electron groups around the central atom, you'll notice that the second one takes another position on the triangle. Ooh, that looks vulgar. Don't pause the video there. So now I can't unsee it. God damn it. Okay. Anyway, you're going to have both electron pairs on the equatorial plane. And when I get rid of those, you get something that looks a lot less vulgar, thankfully. So you get the letter T. So we're going to call this T-shaped. There we go. And then there is one more for if we have 3 here. If I take away the third one, you could probably guess which one's going to get removed, and it's this one up here. So if I go like that, boop, there we go. Now you'll notice that all 3 of them are around the central plane. Somebody came up with the, I was thinking about, like, what sort of inappropriate term can I give this that also begins with T, and I couldn't think of it. If I have 5 electron groups and 3 of them are electron pairs, and I remove that, now it looks like a line, doesn't it? So we're going to call it linear. So interestingly enough, the only way that you can get linear in molecules with their shapes is if you only have 2 electron groups, or if you have 5, but 3 of them are electron pairs. Which is kind of weird to see. But that's how the models just work out. All right. Finally, let's do 6. So 6 is octahedral. We're only going to do up to 2 because you'll see why. Past that point, we just start getting duplicates. So let's get rid of all the lone pairs. We'll put in all the bonds. So here's 6. Octahedral with nothing but bonded atoms is still octahedral. So nothing really special happens there. If I get rid of one of them, here's my electron pair. I can pick any side, they're all equivalent. But then I go like this, boop. It no longer looks like an octahedron. In fact, there's a flat bottom to it, right? It looks kind of like a square pyramid. So I have a square base and then a pyramid. So we're going to call it that, square pyramidal. And then finally, if I do that for one more, my electron pairs go opposite each other because they repel each other the most effectively. The electron pairs want to be as far apart as possible. And then if I get rid of those, you'll notice, oh, there's the square that we were looking for all along. So this is how you've been drawing all your Lewis structures the entire time. It's just at 90-degree angles. Well, it turns out the only way to get 90-degree angle squares in models is if you have 6 electron groups and 2 of them are electron pairs. So this is square planar. Now, if you go past this, and keep adding things, you'll notice that we end up getting shapes that we've seen before already. So we just don't name them. I'm trying to spin this. There we go. So there's T-shaped. And then linear again. So you can get linear with 4 things around it. And so on and so forth. So that's the Phaet molecular geometry simulator. What you can now do with this is if you go down here to where it says, I gotta expand this again. If you go to the bottom where it says real molecules, then what you can do is you can spin actual molecules around and then try and predict their electron geometry and molecular geometry. So let's use our chart to do that. So how many electron groups are around H2O here? Well, you could see that there are 1, 2, 3, 4. 2 of them are bonds, and 2 of them are electron pairs. So I gotta make a new layer. Hold on. There we go. So for water, I have 4 electron groups. So its electron geometry should be tetrahedral. And look at that. Of those 4 electron groups, 2 of them are electron pairs. So what's its molecular geometry? Well, we say it's bent. And there you go. And if I get rid of the lone pairs, this is what it would look like. So that's what water looks like. This is why you see water drawn in this orientation all the time, because the other electron pairs on oxygen force it into that configuration as opposed to a line. All right, we're going to put another one up here. Let's put CO2. Here's CO2. I realize part of it is hidden. So for CO2, how many electron groups are around the central atom? Hint, I'm scrolling up for a reason. Hopefully you've counted that there are just 2 of them. And if there's 2 electron groups, it doesn't matter how many electron pairs there are, it's always linear. And you can tell that just by looking at it, right? All right, let's do one more example before we take our break. Okay, so this is XeF4. This is xenon tetrafluoride. How many electron groups are there around the central atom? There's obviously more than 2. We'll just scroll down. So there are 6 electron groups. 4 of those are bonds. 2 of them are electron pairs. So the electron geometry of this is octahedral. How many of those are electron pairs? 2 of them. The molecular geometry must be square planar. All right, so you get the gist of how to do this now. So play around with this website and try and predict the geometries of the models. Because what we're going to do when we come back is I'm going to just give you a formula. You're going to have to draw the Lewis structure yourself and then predict the geometry. Okay, so we're going to go take our break. And we'll be back in 10 minutes. Once I could find the timer. There it is. It's hiding somewhere. Oh, there it is right there. So hold on. All right, we'll start the timer, and I'll see you in a little bit. Whoops! I had it on the wrong screen there, and then it reset everything, so. Alright, so this chart that you can see on the screen here. Let me turn off my music real fast. Oh, that's the soundtrack that I'm listening to. Haha. There we go, back to this. This chart that you can see on the screen, although I can't quite fit it all there. There we go. This is going to be really helpful to you. So if you don't feel like writing all this down, hit print screen or something, or whatever. Have this handy, because what we're going to do now is we're going to go back over here. Oh, we don't need this anymore. We're going to go back over here. We've already talked about electron pair geometry, which is going to be the family it belongs to, as you can see here, or Vesper Geometry. And then the textbook calls the next... This is what we just generated. Calls the next one thing the molecular structure. I call it the molecular shape, or the molecular geometry, or stuff like that. And so those terms are these right here on the far right, the molecular geometry for a molecule. So I'm going to give you a molecule. You're going to have to draw its Lewis structure. And you're going to assign it both a Vesper geometry, which is which family does it belong to? And then you're also going to assign it a molecular geometry, which is which individual member of which family. So, for instance, if you had something that was 4 electron groups and one of them was an electron pair, you would have a tetrahedral Vesper and a trigonal pyramidal molecular geometry. If you had a 5 electron group molecule and 2 of them were electron pairs, your Vesper is trigonal bipyramidal and your molecular geometry is T-shaped. So, by using this chart, you can figure out what your molecule is supposed to look like and then draw it appropriately. Now, your textbook has all of these things drawn as pictures. Oops. There we go. I personally think that playing around with the model simulator is a more effective way to look at it than just looking at these static 2D images. But now that you've seen what the molecules look like in 3D space and hopefully manipulated them and spun them around a little bit on your own, you could see all these angles here. Now, you'll notice that all the numbers in here match up with what we said before. So there's 180, 120, etc. But then when we start adding in electron pairs, you'll notice, oh, why do I have to start putting in these less than symbols? We're going to talk about that in just a little bit. So don't worry about that too much currently. What I do want you to know right now is the numbers for each of these Vesper geometries. So 2 is 180, 3 is 120, 4 is 109.5, etc. Okay? We'll get to the less than in just a second. All right, so let's suppose I asked you to figure out the molecular structure for ammonia. So we would draw its Lewis structure. And to start, you just draw it however the hell you want to. So draw it normally, which is, you draw this, probably, right? Don't worry about angles, don't worry about the shape or whatever. Now what we're going to do is we're going to count all the electron groups. How many electron groups are around the central atom in ammonia? So there's 3 bonds and an electron pair. So there are 4 groups. What shape is 4? Well, if we go over here, we can see that 4 is tetrahedral. So we'll write that down. So that's its Vesper geometry. Or electron geometry. Either term is fine. Of those 4 groups, one of them is an electron pair. So if I go to the preview problem, what's the 4 family and the member of that family in the 1 position? Trigonal pyramidal. So then we would write that in for its molecular geometry or molecular shape. And so now that I know that, I can then draw my molecule in the correct shape so that it looks like trigonal pyramidal. So that's what ammonia looks like. All the H's are kind of pushed away from the electron pair, and they're not flat in the same plane. So that's our objective here. First, draw the Lewis structure however you do it, with no regard to accuracy, that's fine. Then count the electron groups, figure out what the Vesper and molecular geometry are, and then redraw the molecule if necessary so that it matches the expected geometry based on what we were playing around with in the model viewer. All right. Now, when you're drawing your molecule and you have non-bonded electron pairs, make sure that the electron pairs are as far apart as possible. Now, this particularly happens on trigonal bipyramidal. So here I have two electron pairs that are 90 degrees apart. Here I have two electron pairs, though, that are 120 degrees apart. Since this is the further arrangement, this is the observation we make. Electron pairs actually are more powerful at repelling than electrons and bonds are. And the reason for that is because in a bond, my electrons in the bond are between two nuclei, so they want to stay kind of in the middle region, like in here. They don't want to go out to the far sides here. But these electrons for our non-bonding electrons can go wherever really they want to. They have a larger region that they can influence, even though they are smaller. I just realized that I put a check mark down there, and that's not what I meant to do. So this is what we observe, but this is not what we observe. So our electron pairs will go as far apart as they can. So if you're ever trying to figure out, okay, where do I put my electron pair on this structure? Because I need to remove a bond and replace it with an electron pair. If you get up to 5 or 6, this happens with 6 also, put your electrons in positions that are as far apart from the first electron pair as you can. All right, so I'm going to give you about 5 or 6 minutes to do as many of these as you can. And then we're going to go just like type the structures into, or I'm going to just draw the structures really quickly. And we'll predict their geometry in the model viewer. So try any number of these. You don't have to do the first one first. Do it in any order you want. But I am going to give you about 5 minutes to do these. We'll go over the answers in just a bit. See you in a second. All right, 2 more minutes and we'll go over the answers. All right. I wish we had more time for this, but unfortunately I don't. Let me get rid of this real quick. All right, so the first thing that we're going to do is I made some more space over here so we could draw Lewis structures. So we're going to draw the Lewis structure for ozone. So remember, for following the 5-step plan, we're going to count valence electrons. So the ozone has 18, because each oxygen is worth 6. I'm going to just draw my molecules like in a line, because presumably we don't know how it's going to turn out. So that's 2, 4 electrons, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I need to double bond something. And there we go. So there's my Lewis structure. Now I'm going to count the number of electron groups around the central atom. So that is, 1 is this bond, 1 is this electron pair, and 1 is this double bond. So there are 3 groups. What is 3 called? We'll go back over here. And you'll see that 3 is trigonal planar. So the Vesper geometry is trigonal planar. And of those 3 groups, 1 was an electron pair. So the molecular geometry is, if we go back over here, 3 electron groups, 1 is an electron pair. We would call it bent. So our structure should actually be drawn bent. So if I corrected it, it would look like this. This is what the Lewis structure of ozone should look like. There you go. So let's do that again. So I'll hit clear here because we're going to run out of space again. So let's do SnCO3. That should be an N. There we go. How many electrons is that? So that's 4 plus 7 times 3 plus 1. So that's 26 electrons. And again, I don't know where this is going to end up. I mean, I do, but... So there's 6 electrons, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay, now we're going to count electron groups around the central atom. So I got 1, 2, 3, 4. So 4 electron groups. What's the Vesper geometry? Well, 4 electron groups is tetrahedral. Forgot the E in there. There we go. Of those 4, one of them's an electron pair. Ah, there we go. So one's an electron pair. What is the molecular geometry? Trigonal bipyramidal. So now we can redraw it in the correct way so that it looks more trigonal pyramidal. There you go. All right. I don't really, I unfortunately don't have enough time to go over any of the remaining examples, but you can see how this works. If you have questions about them, you can ask me in the Discord. But I do need to get started on molecular polarity because we're going to run out of time for the content in this class if I don't keep going. What I can do is I will just tell you the answers here, though. So Vesper geometry and then molecular geometry. So we just did the first two. So this one's tetrahedral and bent. These are both trigonal planar. I3 minus I have memorized. This is trigonal bipyramidal and linear. And I want to say IF5 is square pyramidal and octahedral. Other way around, but let me count real quick. 42, 8, 16, 32, 40. Yeah, okay. So this is octahedral and square pyramidal. And if you have questions about those, I can do them and post the pictures on the Discord, but I do need to keep going, unfortunately, because we only have like 25 more minutes of class today. Now, earlier we were talking about how if you add electrons in, what you end up with are larger and larger and larger repulsions. If I have just bonds, I get a very regular arrangement. But if I replace a bond with an electron pair, what ends up happening is that these electrons push on the other bonds harder than they get pushed back. And as a result, all of the remaining bond angles away from the electron pairs decrease. Now, you don't need to know these numbers. Instead, what you need to know is that for a 4 electron group, 0 of which are electron pairs, the bond angle is what you would expect. But with 1 electron pair or more, we would say it's less than what you would expect. So these are the angles that I would ask you to report if I was giving you a question like this on the quiz. Hint, hint. I might ask you, draw the Lewis structure for ammonia. What are the bond angles? And then you would check the box that says less than 109.5 degrees. Make sure you understand what less than is. The alligator eats the bigger number, right? All right. Now, it's not just electron pairs that do that, but double bonds do that too. Triple bonds as well, although with a triple bond, we've used up most of the electrons around a central atom, and you end up with a linear anyway, so. If you were given this structure, what I would say to do first is, okay, well, these should all be about 120, right? But then I would say, okay, well, if there's a double bond here, these become greater than 120, and this becomes less than 120. And the reason for this is because double bonds have twice the number of electrons, so they push and repel harder than the single bonds do. And again, you do not need to be that specific. You just need to use greater than or less than as appropriate. But make sure that you use, the correct symbol. Don't accidentally write less than when you meant to do greater than. Now, if I give you a big molecule, like this molecule is not drawn correctly. First of all, the electrons are missing, so we'd have to fill those in. That would be a little bit challenging for you to do, but you've probably noticed now that nitrogen commonly has one electron pair and oxygen commonly has two, so you can do a little bit with that. But now that I've done that, and I asked you, what is the shape of this? Are all these atoms in a line, this HNCCOH? Or is the shape different? And you should be able to identify, well, okay, the first molecule right there at position number 1 is tetrahedral for Vesper, and for the molecular, it's trigonal pyramidal. So that's absolutely not going to be in a straight line. For position 2, there are 3 electron groups around it. So this is going to be trigonal planar. And none of them are electron pairs, so the molecular shape is also trigonal planar. At position 3, there are 4 electron groups around it, so that's tetrahedral. And none of them are electron pairs, so my pen is like getting stuck on the board here. There we go. So also tetrahedral. For position 4, there are 1, 2, 3, 4 electron groups, so that's also tetrahedral. But 2 of them are electron pairs, so that part is bent. So we could draw a molecule that meets all of these specifications. So position 1 needs to have a tetrahedral, trigonal pyramidal, and then position 2 needs to have trigonal planar, so I could do this. There we go. Notice I had to invert it. That's really the only way I could make it retain the triangle. Totally all right. And then this would have an H going up here, and then something like this, so that this one could go that way. O, like that. So you'll notice that going through the middle, it's more of like a zigzag, as opposed to a straight line. This is extremely common in organic chemistry, is that when you connect a bunch of molecules together, we call them linear even though they draw a zigzag pattern. So you're going to see the zigzag a lot, and it is due to all of the angles that are constructed when you make molecules with these more complex geometries. So whenever you need to identify the geometry of a molecule that's more than just one central atom, assign a geometry to every central atom, and then do the best that you can. Obviously, I'm not going to make you draw something into Canvas. But I could put a molecule like this on the board and say, okay, what's the geometry around position 3? That's definitely in bounds. All right, now you could do the bond angles for that as well. So because we know what the molecular geometries were, we can predict these. So remember that electron pairs push stuff away further. So bond angle 1 is going to be less than 109.5. Bond angle 2 should be 120 because it's trigonal planar, but remember, double bonds push away too. So if this is bond angle 2 right here, then this will be less than 120. Nothing unusual happening around number 3, so bond angle 3 is 109.5. And then bond angle 4, this one right here, it looks like it's 180, but it's not. And then remember, these electron pairs are pushing these bonds away as well, less than 109.5. So associate an angle with a geometry, and then you'll be in good shape. Now, down here, you should immediately notice that something looks wrong. And the reason for that is if I look at this, and I count the number of electron groups around my carbon, I get 2 groups. And for something that's linear, remember that linear is 180 degrees. Well, I didn't draw it like that, did I? So there must be an issue here. And the issue is that this should all be in a line before we hit the tetrahedral part. All right, that's geometry. So what I want you to do is I want you to draw as many Lewis structures as you can from not just this section, but from the homework text as well. And practice applying a a Vesper geometry. So going back to this right here. Practice applying both a Vesper geometry, which is the first name, and then a molecular geometry, which is the second name. Okay? And then try drawing your Lewis structure to the best degree of accuracy that you can. Okay? That's going to be very important for tomorrow when we talk about polarity, because polarity involves geometry very, 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 very carefully drawn. Hold on just a second. Let me save this real quick. So desktop, PNG. So what I'm going to do is I'm just going to save this picture. And then we're going to drop it straight into the Discord. Somebody has already done this for me, but we'll do it anyway. So add picture. It's just called lecture setup because that's just what I named the thing. So, and there we go. So that chart that I just made is now in the Discord in case you need it. Okay. I don't have enough time to start talking about polarity, but I will just very briefly what we're going to be doing tomorrow, and this is going to be complex, so I really need people to go and practice geometry tonight so they have a good grasp on it. Which pushes harder, double bonds or unbonded pairs? That's a good question. I would have to answer that experimentally. So I would say that you are not really going to hit a situation where you have both. And if you do, I would say that non-bonding pairs probably win overall because they just have a bigger range. But I actually don't know the answer to that. My best guess is that non-bonded should be the ones that win. Although when you get to like triple bonds and stuff, that gets a little bit more complicated. So let me just briefly talk about what we're going to do for polarity. So the next thing that we're going to do is we're going to look at geometry and apply the idea of electronegativity to it. So for instance, if I have a water molecule and I draw my water molecule with the correct geometry, you might remember back in early chapter 4 where we said, oh, okay, well, if I calculate the electronegativity difference of this, I could figure out what the difference in electronegativity is. And I could assign that as an arrow. Okay, there we go. There's my polarity. I do the same thing over here for this bond. What we're going to do tomorrow is we're going to assign an overall polarity by doing vector addition. And I'm going to show you how to do it graphically. We're not going to do it mathematically. But we're going to see that overall, on my water molecule, those two vectors should end up summing together to make something that looks like this. All right, so that's where we're going tomorrow. Are we going to have enough time to cover Chapter 5? Chapter 5 is actually like 10 slides, believe it or not. I don't know why Chapter 5 is so short when Chapters 3 and 4 are so goddamn long. Whoever wrote this textbook is obnoxious, but yeah. Also, your cat says hi because they're typing in the thing. All right, so that's where we're going tomorrow. Triple equals unbonded. Okay, that's cool. I didn't actually know that. That will never come up in this class. I really just want you to write greater than or less than, and that'll be good enough. All right. That is it for today's lecture. So tomorrow when we come back, we will finish Chapter 4 because there's only 2 topics left. We're going to do polarity and we'll talk about intermolecular forces. And then what I will do is I'm going to look and see how long it will take me to cover the Chapter 5 content. Because it is very, very short, believe it or not. We don't do half of it. I don't do molecular orbitals. We just talk about hybridization and sigma and pi bonds, which I could probably do in 20 minutes if I absolutely needed to. So that might get pushed to the review day. But I will look over that. We will get through all of the material one way or the other. But yeah, we're at the very end of the quarter. We are just going to cram some stuff in, unfortunately. This is how every class goes, is, oh shit, we spent too much time on practice problems, so now I have to cover certain topics really quickly. But you'll review these in Chem anyway, so it's not really a huge deal. All right. Please let me know if you have any questions in the Discord. I suspect there's going to be lots of questions about all this content. We're going to meet again tomorrow for what should be the last lecture. because Wednesday will be a review session, although I might have to do a little bit of lecture on Wednesday. So yeah, I will see you then for that. Until then, take care, and I will see you tomorrow. Have a good one.